In this lesson, we shall focus on Math 142, MATH 142, a UKZN module, center of gravity, and centroid calculations. Right, we shall do a lot of practice. We shall solve a wide range of problems. Now, the basics have become a little bit familiar in terms of the objectives, which we has spent time on, the chapter outline, the center of gravity itself, which obviously was determined, the center of gravity, the center of mass, where you have the summation of the mass. All right, today we shall spend time solving problems, and we shall share a lot of problems, and also the centroid of a volume for the three-dimensional shapes. Right, we shall actually spend a lot of time doing lots of the practice, the centroid of an area as well for the two-dimensional shapes like a plate, a shell, and so on. And we shall look at a wide range of problems where we practice. And the centroid of a line was actually of the greatest interest. But you know, when you look at the centroid of a line, just to recap on that, but also to explain the several things that became relevant. Now, locate the centroid of the rod bent into the shape of a parabolic arc. We looked at that. Here is a rod bent into the shape of a parabolic arc. The equation of this rod is x equals y squared, and we have the x tilde, y tilde as well, and we have the c with the component x bar, y bar. Okay, now we're actually able to realize that you can actually be in a position to use the fact that if you actually know how to deal with the necessary differential, right, on the vertical you have a dy, the horizontal is the dx, and this is a right angle triangle, and this becomes dl. And if the triangle is right angled like this, we're able to note that we can be able to use the Pythagoras theorem, right? Vertical is dy, horizontal is dx, and this is dl. Okay, Pythagoras theorem tells us that dl is the square root of the dx squared plus dy squared, and it becomes exactly this that we saw. But what was of interest was to then verify these here. Okay, so to verify these, it became something very important, and we spent a bit of time on that because it was, I'm sure, of great interest to you. For example, right, if you look at the fact that now we looked at the fact that now the x bar can be seen as the following, right? It can be seen as exactly the integral of x tilde, and we have dl, the integral of dl here, the integral dl ll, like this. Right, so, and as a consequence, what then you're getting is the fact that we are then able to take note of a couple of things, but it is the fact that the x tilde itself, it's x, and the y tilde is y. And this, how do we know this? It is actually what was given in the question, that x tilde, y tilde is y, and x tilde is x. What is this? Well, the x tilde and y tilde become the sort of arbitrary positions, or positions of arbitrary particles of the structure under consideration. And we're able to see that the y tilde is y and x tilde is x. Okay, so, and with that mentioned, we're able to then proceed to then say this is the integral of x dl. And what is dl? dl, we know very well that it is actually exactly the square root of what? Right, it is the square root of the dx, and that, but we're able to see that it is the square root of 4y squared. Right, so we're able to see that it is the square, dl is the square root of 2y squared plus 1 dy by using Pythagoras theorem, but also using the fact that dl is the square root of dx dy squared plus 1 dy, but also using the fact that x itself is y squared, and therefore dx is 2y dy, and therefore dx dy is 2y. We square this. It means that wherever there is dx dy, we can put our 2y there, and we square that. But okay, with that squared, it means that for wherever it is dl, we have the 2y squared, which becomes 4y squared plus 1 dy. And we divide this by the integral, right? The integral of what? The integral of the dl, which is exactly 4y squared plus 1 dy. Now, what exactly needs to be noted here? Right, it is the fact that for this particular rod, x is y squared, so that wherever there is x, we actually would be able to put y squared, and we have the square root of the following, which is the square root of actually 4y squared plus 1, and you have the dy. You divide everything by the integral of the square root of 4y squared plus 1 dy. Like so, and I want us to spend a bit more time here and just you know, explore this, but also determine this, because we can be able to do this manually. For example, right now we need to do the numerator at the time, just to avoid, you know, carrying everything forward, writing all the steps. So now we're going to then say we need to consider the integral of y squared, the square root of 4y squared plus 1 dy. And like we saw, we let y be the same as what? Okay, we want the 4 to become a 1, like to be the same as this number 1. And for the 4 to become a 1, we would multiply it by 1/2 squared tangent of theta. And this means whenever you have dy dx, rather dy d theta, right? So whenever we have dy d theta, it is 1/2 the secant squared of theta, which means that now at this point, we're able to get what we actually need. And what then do we need? It therefore means that at this point, we can then say thus the integral of y squared, the square root of 4y squared plus 1 dy, which is the integral of the y. What is the y? Right, so wherever there is y, you put this guy, and it is actually 1/2 the tangent of theta, and you put the square root like this. And now the 4y squared, we would have the 1/2 the tangent of theta, u square plus 1. Okay, there's a 4 outside. Let's just put that one. Let us just put that one. Right, so the 4 1/2 tan squared theta squared plus 1, and what is dy, which is sec squared theta, d theta, like this. Right, so this is what we are able to achieve. But now, what exactly is the meaning of everything here? So this is the integral of 1/2 the tangent of theta, right? In which case, therefore, would have the u squared 1/2 becomes 1/4, and you multiply by 4, and this becomes tan squared theta plus 1, and you would have 1/2 times 1/2, right? And 1/2 times 1/2, you can write it as 1/4. It's okay like that. You write it as exactly 1/4, then you have the tangent of theta, and then you have the, okay, so this once again is the formula we use. Right, so you have actually here the secant squared d theta, and what then this means, it actually is able to tell us that whenever we have the integral of y squared, the square root of 4y squared plus 1 dy, this integral is actually the same as, right? We have 1/4 the integral of the following. 1/4 the integral of the tangent of theta, and you have the square root, right? You have the square root of the tangent square of theta plus 1, and we then carry forward the secant squared, right? So I know that I've given you this as an exercise because we had done something similar. And now with this then mentioned, we have 1/4 the integral of the tangent of theta, and the tangent squared plus 1 becomes exactly the secant square of theta. And okay, the aim is to evaluate the integral, and then we'll plug in the limits. All right, so this becomes exactly the secant squared d theta, and this is actually 1/4 the tangent of theta. The square root of this one becomes the secant of theta times the secant squared, which is the secant cubed of theta d theta. Right, so now we have exactly this, okay, but now let's watch out because there is a square here. There is a square y squared, right? Because of the y squared, this one must be squared, and this tangent is going to be squared. So if you square because of the y squared here, if you square the 1/2, it becomes 1/4, but you multiply by 1/2, it becomes 1/8, 1/8. So you'd have here 1/8. Right, so you have here 1/8, which is 1/4, and 1/2 becomes 1/8, and we have that. Right, so in which case, therefore, you'd have the 1/8 outside. So you'd have here 1/8, and you have 1/8, 1/8, like this. Okay, and you'd have here 1/8 as well. Okay, pay attention. You have 1/8 also, this part here. Right, so you have exactly that, but yeah, the tangent is squared, and it's going to be squared there. Right, now at this point, we need to evaluate this particular integral. The question then is, how do we evaluate this particular integral? Right, and we look at this and think and reason. If you let u to be, for example, the tangent, the derivative of the tangent is the secant squared. Right, so, and that means that we really can be in a position to evaluate this integral very carefully. But now you need to be very cautious of the best way to integrate this. So in any case, then, if you break the secant cubed and you have the secant squared, so you can be able to evaluate, for example, one part of that. Right, so now, what other method can we employ to actually evaluate this integral? Now, you need to pause and reason. And now, there are a couple of techniques that are normally used to evaluate these particular types of integral, right? And so you need to think very, very carefully. Okay, we're going to just evaluate it right now. And in evaluating this particular integral, if you have the secant cubed, right, so we have with us here the secant cubed, and we have also the tangent squared. Okay, let us look at this together and reason, because I want us to be very, very to have a clear objective in terms of what needs to be done to actually evaluate this integral. So the best way to evaluate this integral is to break the the tangent squared. Right, so we're going to separate, okay, that's fine. We're going to separate the tangent squared. And with that means that if you ever have the integral of this one, so now integration requires a very cunning eye. Otherwise, then you find yourself wallowing into more challenges to integrate the function. So we're going to look at the fact that the tangent squared itself is the same as what? Tangent squared is the secant squared minus 1 secant cubed theta d theta, like this. And what is this? This is actually 1/8 the integral of the secant to the 5th power of theta d theta minus 1/8 the integral, minus 1/8 the integral of the secant to the cubed. Right, so you're going to have the cube here. Right, so once you have a cube here, the theta like this. Right, so yeah, you have this. But now, what exactly are these integrals here? So these particular integrals can be evaluated with so much ease as follows. Now, first things first, we shall consider one of them. Like, let's consider the integral of the secant cubed theta d theta. Right, and to evaluate this integral, we actually took a look at this last time. And one very clear objective is to break this into parts. Right, and if you break it into the secant squared theta, the secant of theta, d theta, right, or you can put the square here and then put the first power here. Okay, and this, what is the meaning of this? Okay, the meaning of this therefore becomes the integral of the secant squared. Right, so and by using integration by parts, you will first find the integral of the secant squared minus the following. Right, so you need to write a little bit more. Let's write at the bottom to create more space. So you'd have the integral of the derivative of this, secant, which is the secant of theta tan theta. And then we have the integral of the secant squared d theta. And then we have d theta, right, which is then the integral of the secant cubed theta d theta, which equals, right, so you have here this one. Now you'd have the integral of the secant squared, which is the tangent. So this is going to be sec theta tan theta, right? So this is going to be exactly sec theta, the tangent of theta, right? It's going to be sec theta tangent of theta, right? Sec theta tangent of theta. And now you then actually would need here a minus. So the integral of the secant squared is going to be exactly the tangent, so that we have the tangent by the tangent, which is the tangent squared. So this is then minus the integral, right? So this is exactly minus the integral of the secant of theta, the tangent squared of theta d theta. So you have the secant of theta tan theta. Okay, you have this one. The tangent squared is what? Right, so the tangent squared, we know that from metric, the tangent squared theta plus 1 is the secant squared theta. So that in the place of the tangent squared, you can put the secant squared minus 1 d theta. Right, and with that mentioned, we good. We used the grade 12 property of or the grade 11, the high school stuff, as a property of the trigonometric functions, meaning here, we have the secant of theta, the tangent of theta, minus the secant cubed theta, d theta, plus the integral of the secant of theta, d theta. Okay, yeah. And then now we have the secant cubed and the secant cubed, and then now if you add this one, it becomes double the integral of the secant cubed theta, d theta, which equals the integral of the secant of theta, tangent of theta, plus the integral. Okay, what is the integral of the secant? Right, is the natural log of the secant of theta plus the tangent of theta, and you add an arbitrary constant C1 of integration, meaning the integral of the secant cubed theta d theta is 1/2 the secant of theta, the tangent of theta, plus 1/2 the natural log of the secant of theta plus the tangent of theta, plus now c the constant of what? The arbitrary constant of integration. So take a look at this. This would be the integral of the secant cubed. Now, let us keep this one in the meantime. Now, with this, then we proceed to look at the other one, because you'd remember that when we got to this point, we were able to achieve two things. First, the integral of the secant cubed, but also the integral of what? The integral of the secant to the fifth power. So we're going to look at the integral of the secant to the fifth power. So the integral of the secant to the fifth power of theta d theta is the same as the integral of what? Right, so we can be able to integrate this one and you break it into parts. Right, so obviously now the question becomes, what is the best way to actually perform this particular integral here? If you have this integral, what is the best way to actually perform this one? And what is the best way to solve this particular integral? So if you have the integral to the fifth power, so what do we do? What do we do? What do we do? What do we do? Okay. A couple of things therefore become very, very important for us to obviously break this one into components. But first things first, we're going to actually break these into the secant squared and the secant cubed. Right, so if you look at the secant squared theta, and then you have the secant cubed theta d theta. Okay, let's pay particular attention to this. And the question then is, how can we then be in a position to evaluate this particular integral over here? And what exactly do we need to do at this point? And you need to obviously look at this and think very, very carefully in terms of what needs to happen. But also, if you look at the integral, can we use integration by parts? So, or can we use anything different? Can we actually use any form of grouping, etc.? So you need to obviously look at this and think. Right, now, these kinds of integrals themselves take a considerable amount of effort, but also order and discipline, right, to be in a position to get the result. And so let's look at this. One thing you can be able to integrate is the secant squared, because the integral of the secant squared becomes the tangent, right? And then now you'd have again the secant cubed. And so the question then becomes, what then becomes the best way to evaluate this particular integral? Okay, so you need to think, but you need to think very, very carefully and see what more you actually can be able to do. And right, keep thinking, keep thinking. Now, if you actually, for instance, are looking at this in front of us, how best can it be integrated, but also what sort of methods actually serve very well. So, I mean, I'm looking at this and I want us to be very objective, because in integration is not advisable to just do anything without reasoning, because then you'd have a bit more, you'd waste your time. Yeah, good. So, right, so we can just be in a position to integrate this power using integration by parts, saying this is sec cubed theta, and you have the secant squared here, like this, minus the integral. Right, so in this case, therefore, we find the derivative of this. Right, the derivative of this becomes 3, the secant squared theta, and the derivative of the secant becomes the secant of theta, tan theta, and then we have the integral of the secant squared theta d theta d theta. Right, so the integral of the secant squared becomes a tangent, so that this is secant squared theta, tan theta, minus, okay, so you have the 3 here that comes out of this, but the integral of the secant squared becomes the tangent. Right, so at this point, then this would be 3, and then you'd have the secant. So now this is secant squared times the secant, which actually becomes the secant cubed. Theta, the tangent times the tangent, becomes the tangent squared theta d theta. Okay, because the integral of the secant squared becomes a tangent. Okay, there's another tangent there giving us the tangent squared. Okay, let's pay particular attention to these and look at what we can do next. Right, so there are a couple of things, obviously, that remain very, very key here. But what remains very key is the fact that from metric, we know something. We know that 1 plus the tangent squared of theta is actually equal to the secant squared of theta. Okay, we know this from metric. Now, with this, then it means that if you have the secant of cubed of theta, the tangent of theta, minus 3, then you have here the secant cubed theta, the tangent squared is the same as the secant squared theta minus 1, and we have d theta like this. Right, and what is this? This is the secant cubed theta, tan theta, minus, so you multiply this out and it becomes minus 3. The secant squared, secant cubed, secant squared would give us the secant to the 5th power. Okay, so if you have the secant to the 5th power, so you have the secant to the 5th power of theta d theta, and then now you actually deal with this, and this is going to be exactly plus 3. Okay, it's going to be plus 3, the integral of the secant cubed d theta, which is the secant cubed theta, and this is the tangent of theta. Right, so minus, now these 3 can be taken across, giving us exactly 4, the integral of the secant to the 5th power, like this. Now, okay, so this one we've moved it across, and then we have a plus 3, the integral of the secant of theta d theta. Right, and with this mentioned, what then are we able to, as a matter of fact, achieve here? So what we're able to achieve is the fact that we've already got the secant cubed. So we've got that we have 4, the integral of the secant to the 5th power of theta d theta, which equals secant cubed 10 theta. Right, so plus 3, the integral of the secant cubed. So in the end, then you have the following. So this is the integral of the secant to 5th power, which is 1/4 the secant cubed 10 theta plus 3 out of 4, the integral of the secant cubed d theta, which is the integral of the secant to the 5th power of theta d theta, which equals 1/4 the integral of the secant cubed 10 theta plus 3 out of 4. Okay, then what is the integral of the secant cubed? We have already got the integral of the secant cubed. Right, the integral of the secant cubed is 1/2. 1/2 of the secant tangent, and 1/2 the natural log. Right, so we use that. We use that here. So this is 1/2 the secant of theta, the tangent of theta, plus 1/2 the natural log of the secant of theta, the tangent of theta, like this. Okay, and then you add c, arbitrary constant of integration, so that this one is that, which is that, the secant cubed theta 10 theta plus 3 out of 8, the secant theta 10 theta. So in which case, therefore, we're able to see exactly what we're getting here. And this then becomes the following. Becomes exactly the following. So, right, so this is going to become also plus 3 out of 8, the natural log of the secant of theta, the tangent of theta plus c. Let's check this one. Check, 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 check. Right, so we have exactly these here. Are there any like terms or anything like that? So you need to look at these very carefully and check if you have any like terms. But obviously, we do not appear to have any like terms. And therefore, this is actually what then remains very important for us to take into account. And okay, we have already got the integral of the secant to the fifth power. What then is the advantage of this here? The advantage of this is therefore that we go back to the integral we had. So which means the integral of the y squared, the square root of 4y squared dy, is actually these two things. So which means whenever you have the integral of y squared here, right, so the integral of this is actually the same as what? Which is 4y squared plus 1 dy. Right, so this integral here, right, the integral of the y squared, like this, it is actually 1/8 of the secant to the fifth power d theta minus 1/8 of the cube. So let's look at that. Okay. 1/8 of the integral of the secant to the fifth power d theta minus 1/8 of the integral of the secant cubed theta d theta. Okay, so this one here becomes exactly 4y squared plus 1 and then dy, right? So let us pay particular attention to this, but also see how best we can do this. So it's 1/8. What is the integral of the secant to the fifth power? Right, it is 1/4 the secant cubed, tan theta. 1/4 the secant cubed, tan theta. 3/8 of the secant theta, tan theta. Right, so this is actually plus 3/8 of the secant theta, tan theta, of the secant theta, tan theta. And what else? Plus 3/8 of the ln of the secant plus the tangent. Plus 3/8 the ln of the secant of theta, the tangent of theta. Right. So this is exactly for this part. And then we have minus 1/8. Right. What is the integral of the secant cubed? So the integral of the secant cubed is going to be exactly the following. So the integral of the secant cubed, we've already seen it. It's having some halves. So this integral is 1/2. You can write 1/2. The secant of theta, the tangent of theta. And then you also, well, you can write also 1/2 the integral of 1/2 the ln of the secant of theta plus the tangent of theta plus c plus c plus c. So it's for this one plus c. Right, meaning whenever you have the integral of the y squared and then we have 4y squared plus 1. Right, so now let's look at the secant cubed, which is 1/1616, which is 32, the secant cubed of theta, the tangent of theta. So now if you have this one, 3/8 and minus 1/16, because 8/2 is 16. What's the answer to this? Right, so if you're dealing with 3/8 and you have minus 1/16, take 16 as the LCD, you divide 16 by 8, getting 2 by 3, 6 minus 1, which is 5/16. Right, so yeah, you see, it's going to be 5/16. Okay, because we're dealing with what? We're dealing with, okay, there's 1/8 for that multiplies the secant to the 5th power, but it's also minus 1/8. Okay, so this one, the sec cubed tan theta is the only one of its kind. But now there's this one here. Okay. Okay, there's a bit more than meets the eye. Right, because in the end, then you'd have the following. Let's just do it properly. All right, in the end, you'd have the following. Okay, so yeah, we have this one here, which is 3 out of 64. If you multiply this with this, and then with right, you have this with that, which is 3 out of 64, and then this with that, which is minus 1 out of 16. Right, this is like 8 by 8, and this is like 8 by 2. So you can just take 8 by 8 and divide this by that. You get exactly what? You get exactly 1. 1 by 3 gives us 3 minus. If you divide this one by 8 by 2, you'd have exactly what? You'd have 4 by 1, which is a 4. And this is minus 3 out of 64. Okay, so it's going to be exactly for this. So it's minus 3 out of 64. The secant of theta tan theta. All right, so you have this one, which is 3 out of, again, same thing. So in that, it's going to be exactly minus 3 out of 64. The natural log of the secant of theta, the tangent of theta, plus c. Okay, let's check. Okay, we have already got this one. Now, with this, then you can be in a position to go back to the problem and just evaluate this. Because I'd given you this as a homework. So now, remember that for this part, the y squared, the integral is the integral from 0 to 1. Right, so, but also, yeah. We remember last time that we said we're changing the variables. So the y is from 0 to 1. And then if you have y equals 1/2 the tangent of theta, and this means that you'd have that the y becomes 0. Okay, at 0, 0 half tan theta, and theta, this becomes 0, and therefore this is going to just be 0. Okay, because you multiply here, becomes the arctan 0, 0. Okay, now if you do the 1 equals 1/2 the tangent of theta, so now we're making y 1. So now we have the tangent of theta. So now you have this one theta. Right, this one we actually were able to get that one last time, but we have a chance to just use a calculator again because I'm sure that we sort of forgot what it was. But by using a calculator, then we're able to get the actual result. Right, so what exactly are we getting? Right, so what are we getting? So we're getting the fact that now we need to do this one, so we need to do arctan 2, which is 1.107. 1.107. Okay, let's check. 1.107. Okay. So we come here. Okay, so in other words, now we need to integrate this one from 0 to 1 of y squared, the square root of 4y squared plus 1 dy. We already know that it is actually the integral we've already got, which is this one, 1/32 secant cubed tan theta 1 over 32, the secant cubed, theta tan theta. And then you have minus 3 out of 64, the secant theta tan theta. Minus 3 out of 64, the secant of theta tan theta. And then we have minus 3 out of 64, the ln. Minus 3 out of 64, the ln of the secant of theta tan theta. All right, this is actually performed. It's integration that is done systematically. I've already done this, and the integration is done from 0 to 1.107. Right, so it's done exactly from 0 to 1.107. Meaning this integral here, we have this one here, dy, 1 over 32, the secant cubed of 1.107. And then we have the tangent of 1.107. 64, the secant of 1.107. The tangent of 1.107. Minus 3 out of 64, the ln of the secant of 1.107 plus the tangent of 1.107, close like this. Okay, this is like the absolute value around the secant and the tangent summation. And then now with this, so yeah, we've taken all this. So it is substitution by this, and then we subtract substitution by 0. 10, 0 is 0, 10, 0 is 0, and then here the 10, 0 is 0, but the secant is of 0 is 1, and therefore the ln of 1 becomes 0. So substitution by 0 is going to produce zeros here, so it's like 0. So now we just need to use a calculator for this, and therefore it will give us the correct estimate. Let's actually use our calculator. Let's just bring that aboard. So bringing the calculator here, then we're able to get the following. We're able to get the following. So we're able to then say it is actually 1 out of 32. And then you have the secant cubed. So the secant cubed, yeah, it's like the cosine. So you can, it's like 1 over the cosine, that is. So let us do this. So you can say 1 out of 32. Right, so you can say 1 out of 32. Then you multiply these by exactly the tangent of 1.107, you close. And now you divide this by the cosine cubed. Cosine of 1.107, you close. Right, so, okay, yeah. You close like this, then you're gonna do a cube here. Right, so you do this and you raise it to the cube. And then now this becomes minus 3 out of 64. 3 out of 64 times, okay, so this one is exactly what we get here. So we can do this 3 out of 64. Then we have here the tangent. We can do this one. And then I have the tangent of 1.107. Okay, calculator, I remember, I think it was in radians, and I since have not changed the setting last time we did. So it's 1.107. Then you have this. And then we have minus 3. Yeah, okay. minus 3 out of 64 times the natural log of the secant. So the secant of that is like 1 out of the cosine of 1.107. It is my hope that we can be able to punch all these in. And then now we'd have here plus. Okay, it's like the screen is full. Okay, it's okay if the screen is full. We can delete some of the things because yeah, it's like it can't take data, any more data. So we can just do just the first part, then we delete all this because it can't capture more data. So now we have this. So it is actually this, which is 0.488397. Okay, so 0.488397. Let's see, y'all. Okay, so now you then have to subtract this one. So, okay. How many calculators I'm having here? Two of them. Okay. Right. So you have the 0.488397. Right. And then you're gonna subtract this one. So if we can use any of the calculators, we can use any of the two calculators. So maybe we can use this one. We can use this one. Okay, using this one, for example, you're gonna do let's do this part. So this part is gonna be exactly 3 out of 64 times the ln of, right? So that would actually be exactly 1 over the cosine of 1.107. You close, and then you add to this, and then you're adding the tangent of this, which is 1.107. You close. Right, so it appears therefore that the answer we're getting is 0.067. Okay, 0.067. So all right, so we have that. Okay, 0.06765. 65. So you can be able to do this one now. Let's use another calculator to do this. So you have 0.488397 minus 0.06765, which is this one, 0.420747. 0.420, 0.420. Right, so let's clean up a little bit here. We remove this part. So we're removing exactly this part here. So it's 0.0. Okay, let's see the other one. Right, so we're gonna use the other one. So it's 0.420 747. 747. So that is sort of the answer we're getting. Now, let's take a look. Right, so I'm sure that you'd have to check that very carefully, that the calculator might have been, one calculator might have been in degrees. Okay, because let me see what the settings are on the calculators in terms of the degrees or radians. Okay, yeah, we have the radian measure. And so if you have the radian measure, you then need to actually obviously check very carefully to see what, because this is in radians. Let me check the other one, 420, and this one is also in radians as well. And you're subtracting these particular results here. Check 3 out of 64 in the 10 of that. And so let's see, we're trying to check. We're trying to check all the details. 1.107 is actually what you're getting for the y. Okay, trying to check some details here to see what is happening. So that is actually what you're going to have. So the limit of integration is obviously the correct one. And so if you have exactly this part, you would have therefore that this particular integral, the integral that is seen here, is exactly this, and this is exactly that. So this is going to be the cube. So this is 1/8 of the. Okay, let us check here what you're going to get here. So right, so it's going to be 1/8 of this one minus 1/8 of that. It's 1/8 of that. So this one is exactly that, and this is minus 1/8 of this, which is 1/8 of 32 is 1 over 32, so cubed. Okay, and then now we got 3 out of, okay, you can do some quick checks here. Can do some quick checks, in which case, for example, if you have this one, 1 over 32, you add these two guys. Right, so if you multiply these two, then it becomes 3 out of 64, which is 3 out of 8 by 8. And then you subtract, because this is 3 out of 8 by 8. Then you minus 1 out of 8 by 2, which is minus 1 out of 64. Let's check this one here. Let's check this one here. Let's check this one here. Minus 1 out of 64. Minus 1 out of 64. Okay, yeah, this is the typo. So it's minus 1 out of 64, not minus 3 out of 64. Right, so it has rectified that one. So that is what created this discrepancy. So it's minus 1 out of 64, meaning you have a minus 1 out of 64 and minus 1 out of 64 there. And also this one is the same thing. So it's going to be minus 1 out of 64. Okay, right. Now you come to this. So at this point, what you're going to have is this one is 1 out of 64, 1 out of 64. Right, so it's minus 1 out of 64, and this one is minus 1 of 64. So yeah, you then have to compute this. So okay, so yeah, let us just do this. So you need to therefore do this properly and then say you're gonna have 1 out of 32, 1 out of 32, and then you multiply this by the this here. But now you're gonna do the times here, then you're gonna do the fraction. Okay, this one, because there's no secant, secant is 1 over cosine, so you can do it as the tangent of 1.107, you close, and it is divided by the cosine cubed, which is the cosine, right, so you can do some brackets and put the cosine here, and you have 1.107, and then you close, and then you cube everything. You cube the denominator. Okay, like that. So yeah, it's gonna actually cater for this. Minus 164 times. Okay, so this one is gonna be exactly be the tangent. 1.107, you close, and then becomes the cosine of this 1.107, you close, and then what is the answer to this? So it will be 0.628058. Right, so that's what you have. So it's 0.6281. Yeah. So you can do 0.6281. Okay, let us check that one. 0.6281. So it's exactly 0.6281. And then now you minus. Right, so let us use our calculator again to enter this one here. 0.6281, and then you actually would use this one is going to be exactly 1 out of 64, and then you multiply by the lead of the secant. Right, and now the secant, because it's not there on this calculator, then you use 1 over cosine. And the cosine of 1.107. So now you have the plus here, which is 1.107. And then you get the answer, which is 0.02255. So it's 0.0, right, so 0.02255. And then now you're going to just do this particular calculation here. Right, so the question then is, you can even do it at the bottom here. Right, so if you do use a calculator to verify what this is, yeah, I'm sure that it's going to work. So what then you're getting is that you have 0.6281 minus 0.02255, which is 0.60, right, in those digits. 0.60 in those digits like this. Now, if you check, let's check how far we are. 0.60 in those digits. 0.60. Yeah, so it's fine. So you're able to see therefore that obviously because of the rounding off, this integral here has been obtained correctly, which is exactly that. The other integral in the denominator we got last time, and therefore if you want to find the actual coordinates of the centroid of the rod, we've already found the top, so the integral of this is going to be 0.60 and those 5 digits, or those 3 digits, but yeah, it's 0.60, it's 0.6063 because it depends on the rounding off on the way, but also we did the bottom, so in the end then the result is 0.410, and now you also have the bottom. So this bottom is the same because it's 1.479, and the top we did last time by use substitution to get this, and therefore this becomes a result. So this would be by and large the centroid of a rod. Right, so now dealing with the centroid of a rod, what is key here and what exactly are we supposed to do? Right, so now there are 3 things you need to do, obviously, or at least 2 things you need to do to deal with the centroid of a rod. The first thing is to be able to find the x tilde dl divided by the integral of dl, and you have L here like this. And then the next thing is also to be able to find this one, which is the integral of y tilde dl, and then you have this is out of L, and this is actually dl. So now this is the formula used. Simultaneously, you look at what x tilde is. So x tilde, this is the formula we use to find the centroid of the rod. And then now the top is x tilde is what? Is x. And the dl, use the Pythagoras theorem, the dl becomes exactly the dx squared, and the dy, okay, you can put some parentheses like this, and then the dy squared like this. Okay, so this gives us the dl, but once again, we're able to know that the dl can be written differently. You can actually have this, but because x is y squared, you need dx, which is dx is 2y dy, so that in the end then you have the x tilde. What is dl? So dl is this, but now you can pull out the dy out of this. So if you pull out the dy out of this, you take the square root, so it's going to be dy, but now you pull out the dy, it's going to be dx dy, and then you square this plus 1. Okay, so in which case you have this 1 plus dy, 1 plus dx dy squared. And then now then we have the dl, and then this is dy. And then now you have also this one, which is the integral of the dl out of L. So obviously we perform this integration here over L, right? So, and with that mentioned, we have the integral of the dl, and dl is going to be this. So it's going to be exactly this, but now the dx dy, because you have this. So if x itself is y squared, which means that dx dy is 2y, in which case, therefore, it is 1 plus, so this one is x, and therefore this is 1 plus 2y, and then it becomes 4y squared dy, and therefore the bottom, okay, the top and the bottom are they have the square root as well, and you have that. Okay, I'm just elaborating on the actual method that you need to just take note of how we determine the coordinates of the centroid of a rod, of the rod in question. Okay, now I want us to do a lot of practice on the centroids. Right, we shall practice a lot of problems. Let us try a lot of problems. on the centroid. Let us try a lot of problems as follows. Okay, this is the road. I believe the road is quite, a little bit clear already. But what about if you have other shapes like, let us look for other centroids that you need to learn for in this module. Like you actually must be in a position to do the centroid of a triangle, of a rectangle, of a semicircle, of a sector, and so on. All right, so let us actually look at some of these centroids and obviously make the most of them. Right, so now what then do you have here? What then do you have here? Okay, let us look at this. Let us look at this. Let us look at this. Okay, I want us to determine. So now we want to consider. So right, as part of an exercise right now, is we're interested in saying we need to determine the centroid. The centroid of a right-angled um right-angled triangular surface. Triangular surface. Right-angled triangular surface. Okay, let us look at what happens here. Like if you need to be in a position to, you actually have a triangular surface, right-angled. And let us look at these. And I want us to spend time, but carefully doing this. So you need to make sure you understand this because we shall be practically like doing the shapes that are popular in this module. So like your right angle triangle. Now, with that, suppose then you have something like this. X and then Y. Okay? Right, so now what do you have here? What do you have here? Okay. If the base of this triangle, if the base is B, right, the base is B and the height is H. Right, so, and this is making an angle there. Now, you want to find the centroid of a right-angled triangular surface. Let's look at these together. What we do, we perform some constructions. We're going to cut a strip. We're going to cut a strip here, a slice like this. Going to cut a slice like this. Locate a slice that is a rectangle, and therefore we're going to locate its center. And then now, if this one is this particular triangle, so we can perform these constructions here, and then we shall find here dx. Shall find here dx, which is the length, sort of the width of this particular rectangle, and then now we're gonna add this point. identify a point whose coordinates are x and y at the top, at the tip top, but also at the point of intersection of this particular side of the triangle and this particular rectangle. That is those are the coordinates of the point. And then now we're gonna say if okay, these are the coordinates of the point. It means therefore that to move from here to there is gonna be y. Okay, let's just be very, very patient with the shape. I know that it might not look so perfect. So you then have that this length here is y. Right. Simultaneously, you continue to then determine the horizontal length. So if you look right now from here to there, what would this one be? It would actually be on this here, it would actually be x tilde, which is just x. Now, we just call it xy because we know very well that x is, we chose this one to be x. Chose this one to be x, this point, so that from here to there, it's x. Now, the y, which is in the middle, which is y tilde out of 2. Okay? Which is y out of 2. Y out of 2 is like half of this side. So in that, it's going to be exactly y out of 2, which is the vertical displacement from here to there, y out of 2. This will therefore defines the actual center point of this rectangle. Okay. So at this point, we're able to determine the coordinate of the centroid. Because this is a two-dimensional shape, it is an area. Centroid, which is x tilde dA divided by the integral this here, dA. Right, which is the integral of the following. So, which is the integral of the following. So it's going to be 0 to b. Right, so now to find the integral of this, it's going to be 0 to b. Okay, let us pause to reason this out. And what is x tilde? We said x tilde is x. And we have dA. Okay, so let us look at what dA becomes here. Right, let us look at what dA becomes. If we actually obviously are looking at this particular area, right, and we're able to see that the A would become y dA. It becomes exactly y dA because if you consider the differential element, we note that dA here is y dx. This is the differential element. Right, so this becomes the differential element. So that wherever there is dA, you put y dx, excuse. It's y dx. Pay particular attention to that. So then you have the integral. You have the integral. Right, so if you have the integral here, it's going to be 0 to b. The dA is y dx, and the y dx becomes the differential element for the area. It's y dx, differential element for the area. Pay attention. Y dx. Okay, so now the question is, what is y? What is y? Okay, so obviously if this is h and this is b, it means that now on this line, the equation of this line here is y equals h over b minus x, which is the following: xy dx. What is x? What is y? H over b minus x. That is y. And y is that. And then you'd have dx. And you divide everything by the following: the integral from 0 to b. Right, we note that for the x is from 0 to b, and then now you have the y. What is the y? The y is h. The y is exactly h over b minus x dx. Okay, so right, so in the end, then you multiply everything. Xh, x squared. So this would be minus x squared h over b. Right, we're multiplying this out because the b cancels here, giving us only xh, and then now we multiply out, which is minus x squared h over b. And then you have the dx. And this is actually divided by the integral, the denominator, which is the integral of 0 to b. You multiply out, which is exactly h minus hx dx. Okay, so dx. Now what is this? With respect to x, then you can do term by term integration, which is half x squared h from 0 to b. X cubed out of 3 h over b 0 to b, which is hx. Okay, so this one is going to be hx out of b here. And therefore, this is exactly hx from 0 to b minus, this is hx squared divided by twice b. If you integrate the x, the integral of the x, so you remember that the integral of x to the power n is 1 over n plus 1 x to the power n plus 1 plus c. Okay, so we use that fact here. And so now this is actually the integral from 0 to b. And then now we continue. We continue. We continue. Right, so, okay, so let's look at the top, which is exactly b squared h minus b, okay, b cubed So this would therefore become b cubed h over 3b, which is hb minus hb squared over 2b. Okay, so let's check this one. Now, okay, we are checking, and we're trying to see what the best thing to do is here. Right. We continue. We continue. Right, now, the couple of things we need to take note of here. If this is the B, what simplification is possible? Let's take a look at this. What simplification becomes possible here? So the simplification that becomes possible, can we factor out anything? Right? For example, if you factor out, right, anything that can be factorized. So let's take a look at these and reason together. Okay, you can multiply the top and bottom by the B by 6B. So in other words, if you multiply the top and bottom by 6B, what then are we able to achieve here? Right, so let us remove the equal sign. We want to simplify this with so much ease. So we can multiply the top and bottom by 6B, and here 6B. Okay, so we divide this, which becomes exactly 3b cubed h. 3b cubed h. And then this one, we divide 3 becomes 2. Yeah, and then this one, you divide 6 by 3 becomes 2, and then the b cancels out. Okay, so you'd have 2, which is minus 2b cubed h. You divide everything by, okay, multiply here by 6b, which is actually 6hb squared. 6hb squared minus, you multiply through this becomes 3, which is 3hb squared. Now, let us check what we're getting here as a consequence of these things. So we're able to take a look at this and reason. Right. So we continue. Right, so if you look at these very carefully, what really can we be able to take out as a common factor from the numerator? Right, in relation to the denominator. And so let us check very, very carefully here as a consequence. Right. So we continue. Okay, now at this point, if you factor out, for example, the b cubed and the h, okay, these are like terms anyhow. Once again, they are like terms. So if these are like terms, from the 3, you take 2, and then you're gonna have only b cubed h. Okay, these are like terms again. From 6, you take 3, it becomes 3hb squared. And therefore, the b squared removes a 1b here, h cancels, and now you're going to have only b out of 3. Okay, this tells us, therefore, that the x component of the centroid becomes b out of 3. B out of 3. So in other words, if you have this length here, It means the x component is it's going to be just this length here divided by 3, then it's going to take you to the correct so we continue. So also you also have the following. So moreover, you can do the y also. You can do the y as well. Right now, doing the y, we continue as follows. Y tilde. Y bar would be the integral of y tilde dA over A, the integral of dA. All right, so we know that the differential element, right, something we call the differential element. What is a differential element? Would be dA equals y dx. And we note that at this point, the y tilde, right, we note that at this point, the y tilde is what? The y tilde, which becomes the center of a point in the rectangle. It's y tilde is y out of 2, which is the total height is y of this particular rectangle, but you divide it by 2, and therefore it becomes y out of 2, which is y tilde. Right, so at this point, we're going to say what is y tilde? Is y out of 2, and what is dA, the differential element? Is y dx. You divide everything by the integral y dx, which is the differential element for dA. And now we are dealing with the dx here. Dealing with the dx, then we're able to see, therefore, on the x-axis, we're moving from 0 to b. On the x-axis, 0 to b, which means you have 0 to b, and also you have 0 to b. Right, so what is everything that we're getting here? So, and the bottom is similar. Right, right. Okay. So now you'd have to then say y equals, so y equals h over b, b minus x. So now the integral from 0 to b, then you have y squared over 2 dx, and then the integral from 0 out of b, y dx, which is the integral from 0 out of b. And then what is the y? What is the y? So you'd have 1/2 the y, which is the equation of the line, the equation of this particular side of the triangle, which is h over b times b minus x in brackets. So this one is going to be exactly h over b, b minus x, and then you square this, and then you have dx. Okay. So you actually therefore have the integral from 0 to b, h over b, b minus x dx. Okay, so we continue. So now, if you need to integrate this here, What then can we do here? There's a couple of things that we can do here to evaluate this. So first things first, we can pull out the constants, meaning we can pull out h squared, 2b squared, pull it out. Then have the integral focusing on b minus that. You can switch these ones around and have x minus b squared dx. You divide everything by the integral from 0, which is h over b. So you have exactly that. So now then it becomes the integral of, which is h squared over 2b squared, which is that cubed over 3. The integral from 0 to b. You divide by, now you have this, which is actually the same as, okay, integrating this one, integrating the denominator would be the same as minus h over b, x minus that squared over that. Okay, so you substitute this one. Okay, yeah, you put the b here, it's going to be 0. Okay, you put the b, it's going to be 0, then you have minus. You put the 0 in the place of x, which is going to become plus b cubed out of 3, which is minus h over b. You put the b in the place of x, you have a 0, which is b squared out of 2. Okay, so we have exactly this. But now this means that at this point, we have the following. Y bar, which is exactly this here, which is h squared over 2b squared. H squared over 2b squared, open bracket, which is 0 plus b cubed over 3. 0 plus b cubed out of 3, all divided by minus h over b. Minus h over b, 0 minus b squared out of 2. 0 minus b squared out of 2. So this one here is 0. So the b squared, so you can write here h squared 2b squared times b cubed out of 3. You divide everything by minus h over b minus b squared out of 2. So the b squared cancels out here. The b squared cancels out, and the minute it does cancel out, you're going to be left with what? You're going to be left with 1/3. Okay, but the 1/3, there's a 2 here, which becomes like 1/6. 1/6, like 1 out of 6. 1 out of 6, which arises from 2 by 3. But the b, okay, there is h squared, and then there is b cubed over b squared, which becomes what? Which becomes exactly just a b like that. Okay, let us write properly. So in effect, what then we're getting is the following. So the b squared cancels out, giving us just b, and we then have the h squared. You divide everything by, okay, this minus minus gives us a plus, and then you have 1/2, and then you have the h, and then just b like this. Okay, so this is 1/3. So the b cancels out, If B cancels out, you'd have the full H like this. Good. And therefore, as a consequence, this means that for a right-angled triangle, the y component of the centroid is the height of the triangle over 3. So what is then the implication of these things here? Well, the implication of these things here that we're saying is that if we are having a right-angled triangle, and this is x and that is y, this would be h, and that would be b, like this. And then we can be able to find the centroid of this particular right-angled triangle. All right, the centroid can be found by then saying here and there. So this centroid is going to be h over 3, and this one is going to be exactly b over 3. So these become the coordinates of the centroid. The coordinates of the centroid. Okay, so this is very, very important for us. And there's more, obviously, would have a chance to mention, because if we then say that there's more we can say, because now you must be able to, we're going to be actually spending time doing past exams. So if this one, from the distance, for example, from the origin to this point is x, it's b out of 3. Okay, we are effectively saying the whole thing is b, and therefore this one is b out of 3. This one is h out of 3. Yeah. So if the whole thing is just b, then what is the remaining thing? So it's like we're saying from b, take out 1/3 b. From the whole of b, take out 1/3 b. So we put a 3 here over 1, and 3 divided by 1 is 3, and this is 3b minus b, which is 2b out of 3. Which means that if you're closer to the vertex, this is 2b out of 3. In the same way, if this one is h out of 3, it means that here, if you're closer to the vertex, it is 2h out of 3. Right, so this gives us the coordinates of the centroid, but also it gives us the other dimensions that we're able to get from this particular triangle here. So it's something that you need to think about. It's something that you need to think about. Okay, so it is very important for us. Twice b out of that. So we continue. We continue. We continue. Okay, now I want us to continue and do more practice. Like, for example, what would the centroid of a rectangle be? Right, so which is the centroid or geometric center of a rectangle? Right, that is what we're doing next. Let's find, if you have a rectangle. Okay, we're gonna be summarizing these things. But now let us find the centroid. The centroid of a rectangle. Okay. Now we're gonna take a shape like this. We position a rectangle in the first quadrant, like that. And then now we call this one A, units, and we call this one B, units. It's a rectangle where each angle is actually exactly 90 degrees. Each of the interior angles is actually 90 degrees there. Something important. Then we're able to then say, we can cut a strip here like this. Can cut. And if this one here we cut, it is the distance from here to there. What is the distance? It is x tilde, which is just x. And then we can find, we can speak about dA, which is associated with the small area, this small area, if the whole area is A, and then now there is the area element. Now, is something we call the differential element that is going to arise from this. Right, so we continue. We continue. We continue. Right. So we have then the following. So we continue. All right, now let's look at this together. Okay, here's a rectangle and we slicing it up. Right now, if you slice it up, for this particular slicing, if you like, there is a dx, which is this width, like dx. Right, and then we call the distance from here to there exactly x, and then now we can have the right. We continue. Right, so what is this? Okay, let us do this together. So now, the couple of things that obviously you need to take into account to actually be able to get the centroid here. So which means that the centroid of this would be x bar, which is the integral on a x tilde dA divided by the integral of the area d area. Okay, so now this is x tilde. X tilde. Okay, we're still here. Now, if we continue with this, we're able to say, for if we're looking at the fact that the differential element, would be given by the following. Would be given by if this one from here to there, it's the x, and then the length is b. So the differential element is going to be dA, which is like the area of this thing, the differential element. So it's going to be given by exactly the dx, which is like the width times the length, because it's a rectangle. So we can say it's going to be b dx. Okay, that is going to be the differential element. So that at this point, the x tilde will actually, therefore, can be seen as follows. So for the x, we're going to integrate on the x-axis from 0 to a. The x tilde is just x, and the dA is what? B dx. Divided by the integral from 0 to a, and then it is just b dx. Okay. Okay. So what is this? Right. So now we're going to integrate these with respect to x. And then we're going to get, we continue. We continue. Okay, we continue. Okay, so for the x, then it's going to be half x squared b from 0 to a. With respect, it's going to be bx from 0 to a, and therefore this is 1/2 a squared b divided by ab. Okay? So let us see what we're getting. So the b cancels and the a cancels, and if the a cancels, it becomes a out of 2. Right, and this means that we're able to then say that x bar is a out of 2. And then the y bar is the integral of this one, y tilde dA, and now the integral here dA. Okay, for the y tilde, you'd have to consider the following. So you need to consider another case. You can consider another case to make it easier. So we're still looking for the centroid. The centroid of a rectangle. The centroid of a rectangle. In which case, we're going to take this one and just put the same rectangle like this, but we're going to slice it differently. We're going to slice it horizontally right now. Cut a horizontal slice. In which case, therefore, there's going to be a dy, which is the sort of width of this. Okay, take a look at that one. Take a look at that one. All right, so we continue. We want to, we recognize the y and the x. We recognize the y and the x there. So we have this one here, which is y tilde equals y. So in the end, we have y bar, which is the integral, which is y tilde dA divided by the integral over a dA. So we continue. We continue. So now, okay, there are a couple of things that you need to take into account here. Okay, now let's take a look at this and look at the fact that now you're dealing with the y tilde. And now, what would the differential element be here? Right, so you need to focus on the differential element. So we continue. Now, the differential element therefore would be, now if this is dy and then this one is a and then this one is b, the differential element, which would be dA, would therefore be seen as follows. So it's going to be exactly the length times the dy, which is a dy. With that mentioned, it means that now wherever there is a dA, we can put a dy. The y tilde is y, okay? And then you integrate from 0 to a. Okay, so now then what then we're getting here is, okay, it's 0 to b because it's dy, so y is 0 to b. So you need to make this one 0 to b. Make this one 0 to b. Right, and then now also this one here is going to be exactly 0 to b, and the differential element is this by the actual width, which is actually a dy. With respect to y, then it is a y squared out of 2 from 0 to b. And then you have a y from 0 to b. And then which is a b squared out of 2, you divide by ab, and if you divide, okay, now the a cancels out and the b cancels out, being b out of 2, and this is y bar, okay, which is just b out of 2, b out of 2. So now for a rectangle, right, for a rectangle, so we note therefore that for a rectangle we have the following: the centroid for a rectangle, right, is given by, right, so the centroid for a rectangle is given by, so you draw the rectangle, and then now if you draw the rectangle like this, and you call this one A, and if you call this one side B, then the centroid of the rectangle becomes the following. Right, so you're going to have here C, then this one here is going to be exactly B out of 2, and also this one here becomes A out of 2, So now, in other words, to find the centroid of a rectangle, you take the A divided by 2, you take the B divided by 2 also. Okay. Okay. We continue with our study of these particular surfaces. We call these surfaces. Now, let us continue and find more things. Like, what would, for example, the centroid of other shapes be? Okay, we are going on, and the other things we're going to study. Right, so now I want us to do the following. Let's look at this question. Yep, yeah, we are in a good position to study the following. Let us study this shape here. I want us to study this particular shape. Okay, as part of our discussion, I want us to look at composite bodies. Right, in view of composite bodies, this consists of a series of connected, simpler shaped bodies, which may be rectangular, triangular, or semicircular. So popularly, we have rectangular, triangular, or semicircular. And we shall spend time on we looked at rectangular and triangular, but we shall look at semicircular, but also we shall be looking at how to deal with the centroid of a semicircular surface. A body can be sectioned or divided into its composite parts, accounting for finite number of weights. Like if you look at x bar, which is the sum of the x tilde w, and this obviously would be the stuff we discussed last time about determining the centroid linked to the weight, right, or the center of gravity. And therefore now the x bar becomes the x tilde w over the summation of w, total weights. And here this one becomes the summation of the y tilde w divided by the summation of w. The z bar is the summation of z tilde w divided by the, and this gives us the center of gravity. Okay, let us continue. Composite bodies procedure for analysis the composite parts. Divide the body or object into a finite number of composite parts that have simpler shapes. Treat the whole in, so we're going to divide the body into a finite number of composite parts that have simpler shapes. Treat the whole in composite as an additional component but having negative weight or size. Moment arms. Establish the coordinate axis and determine the coordinates of the center of gravity or centroid of each part. Okay, you'll understand what all this means. You don't need to memorize these things. Like composite bodies, the procedure for analysis, the summations. Determine the coordinates of the center of gravity by applying the center of gravity equations. If an object is symmetrical about an axis, the centroid of the object lies on the axis. Okay, if an object is symmetrical about an axis, the centroid of the object lies on the axis. So, all right, this is recorded for control and quality purposes, but I want us to look at this particular example. Locate the centroid of the plate area. So now we're going to be looking at negative area as well. In this case, shall be looking at also negative area, and we shall analyze what that means. Okay, now we're looking at the centroid of the plate area. What is happening here? Right, we're looking at the fact that this particular plate area has a triangle and it has a section that is like somebody's taking a bite from this. Somebody's taking a bite from this, it's like food. Okay, so I want us to continue and analyze what this means. So what we're going to do immediately here is to call this into parts. We're going to call this one 1, component 1, and then this one is component 2, and then this one is going to be called component 3, and we shall imagine this one that is missing, the missing area. Right, so with this mentioned, then we're going to actually now find the centroid of the triangle, then the centroid of the rectangle, and then the centroid of this small piece, the rectangle that is the missing area. Let's look at the composite parts. Plate divided into 3 segments. Okay, we divided the plate into 3 segments. 1, 2, 3. Area of small rectangle considered negative. So the area of the small rectangle considered negative, there's a small rectangle that sits here, but now we have removed it. This one we've removed it. So that then in the end, what the area we have here is half base by height. Okay, well, that would be, but now we're going to continue and find this in detail. But now instead, because there was this part that is missing, okay, yeah. So this part that is missing, then you're going to actually have its own section that is drawn there. So we're going to look at full, because this was like part missing, then we're going to look at the full rectangle. But now, what is the length here? The length is 3, 1 meter, 2 meters, then it's going to be like 3 meters. Right, so if we are looking at the fact that this one is like 3 meters, and this one for the base of the triangle is like 3 meters, but also this is 1 meter, 2 meters, and then it's like 3 meters. So it's 3 meters here, 3 meters up. Right, you're gonna be looking at 3 meters here, and then we also have like 3 meters there. Now, let us look at these together and reason what this means. And reason what this means. Right, so what then we're getting here is the following. We have 3 meters and 3 meters. What would the coordinates of the centroid of a triangle be? We've already said that you need to take the length of a side and divide it by what? And divide it by 3, and also you divide it by 3. So which means that this side here is going to be 3 divided by 3, which is actually 1 meter. And the top one is going to be also 1 meter. So it's 1 meter here and also 1 meter. Okay, giving us exactly this. Now, this gives us the coordinates of the centroid of the triangle. What about the rectangle? If the rectangle is half. So if we know very well that this is 3 meters, then you take the 3 divided by 2, take 3 divided by 2 is 1.5 meters. So this is actually 1.5 meters, but also you know that the top is 3. So you take the 3 divided by 2, which is 1.5 meters. Okay, that's fine. 1.5 meters. Now, let's look at these together. Now, remember that the small little piece here, it's 2 meters here, 2 meters high, and then 1 meter here. So if it's 2 meters and then 1 meter, then you need to divide this particular section by 0.5 because the rectangle you divide by 2. All right, so you divide the 2 by 2, and then you would have a 1 meter. And then divide here, which is 0.5 meter. 0.5 meters, 0.5 meters, 0.5 meters. So you have this. Okay, let us look at this right now and reason these together. So the question then is what we do with this. We use this one to compute the areas. So now we will deal with what I call the moment arm. You would remember something here. That at this point, you have the triangle that is like this. And this one here is exactly 3 meters. And also this top one is 3 meters. You divide by 3, and then it becomes 1 meter, 1 meter. 1 meter, 1 meter. Ah, okay, then you have this one. Okay, so you'd have this section here, which is also 3 meter by 3 meter. But now, if you're dealing with a rectangle, then you're going to find the distance from the origin to there. So now, if you measure the distance from the origin, then it's going to be 1.5, and then it's going to be another 1.5 over there. So this one here is going to be exactly 1.5. And also this one would be 1.5. Right, so we have exactly that. And so now you also have this one, which is the negative area. So the negative area that is, it sits somewhere here. But we know that it's like 2 meters by 1 meter. 2 meters by 1 meter, so that in the end, then you take this one is 0.5 meters. And then this is 1 meter. Okay, if it's 0.5 meters and then it's 1 meter. Okay. You therefore realize that at this point, what you're then getting is the following. So this area, because it was cut, it's a missing, instead of a missing part, this area becomes negative. Let's look at the segments here and the analysis of the moment arms. Location of the centroid for each piece is determined and indicated in the diagram. The segment. Right, so we would remember the segments themselves. Segment 1, segment 2, segment 3. Let's look at segment 1. Segment 1 is this triangle, and therefore the area of a triangle is half base by height. The base of this triangle here is actually exactly 3 meters, and the height is 3 meters. Okay, so yeah, it's half base by height, 3 by 3. Okay, so 3 by 3 is 9 divided by 2 is 4.5. So we continue. And then now here you have this one, which is exactly 3 by 3. So the rectangle, full rectangle here, the area of a rectangle. So once again, this is area of a triangle, which is half base by height. Area of a rectangle is length by breadth. Is length by breadth, so that we have exactly length by breadth. And this is like 3 by 3. Then we have the missing part. And now we then say area of the rectangle considered negative. Area of small rectangle considered negative. It's considered negative because it's missing. So in other words, you would then say now this one of the small rectangle is considered negative because now it's not part of this. So in other words, you then say minus. Obviously, we note that it's 2 meters by 1 meter, which is 2 by 1, like length by a rectangle. So, but it's negative because it's missing. So if you consider all these areas now, the triangle which is half base by height for segment 1, segment 2 is the rectangle, and then segment 3 is this one. Right, so this is 4.5, and then 9, and then minus 2. If you add everything, the sum of these areas is 11.5. Now, there is the x tilde, which is to do with the arbitrary centroids for parts of this, of strips, etc. Okay, right. Let's look at the x tilde right now for the triangle, for the first segment. For the triangle, what is, we realize therefore that if you divide the length, which is 3 by 3, you get 1. So that the x tilde is 1, but also y tilde is 1. Segment 2. Segment 2. Okay, so segment 2 now, okay, would be, we have seen that the rectangle, if this the side is 3 here and the other side is 3, divided 3 by 2, you get 1.5 meter. So now you actually therefore are able to realize that for the x, then you'd have exactly what for this segment 2, the rectangle. So you'd have that for the x then is 1.5 negative, and for the y, it becomes exactly 1.5 up. Right, so it becomes the 1.5 here, negative to the left, and therefore the y becomes 1.5 upwards. Okay, let's look at the segment here. Let's look at this segment. This segment now is 0.5 midway because it's 1, the whole side here, divided by 2 is 0.5. But this segment is also, the whole thing is, it is actually 1 meter, but this is 2 meters. It's like 2 meters. 2 meters. And this is 1 meter. 2 meters plus 1 meter is 3 meters. Okay. So if you then say 2 meters plus 0.5, it's minus 2.5. And then the y is going to go up to the arbitrary centroid of this particular slice, write the missing part whose area is negative, then you then say, okay, upwards is 2 meters, but divide by 2, you have 1. Right, so you have 1 meter. You have 1 meter. Okay, we have 1 meter. Okay, if you have 1 meter, then you're gonna add also. You're gonna add also because this is 2 meters. It's exactly 2 meters here. It's 2 meters, and then this is gonna be 1 meter. So it's exactly 1 meter plus 1 meter, giving us exactly 2 meters. Okay, we have 1 meter here, which is moving 1 meter. And then now this whole thing is 2 meters here. Divide the 2 by 2, this gives us exactly 1 meter. 1 meter plus 1 meter is 2 meters. So in the end, then, okay, now we are finding the products like the x tilde a, because we need to find the summation of the x tilde a, and then also the y tilde a. So we're going to say now the x tilde times a. So it's 1 by 4.5 is 4.5. Minus 1.5 by 9 is minus 13.5. Minus 2.5 times minus 2 is actually equal to 5. Then now you add all these areas. In the same way that you add all these areas, you get 11.5 here. You add also with the negative. And here you add also with the negative. Then you get that the sum of these products is minus 4. Now we have y times 4.5. Which is actually 4.5. And then we have 1.5 times 9, which is 13.5, and 2 times that, which is minus 4. You add all the y tilde a, you get 14. Let's look at the summations. The summations would be the sum of the xa's, which would be minus 4 divided by 11.5. It's minus 0.348 meters. The sum of the y tildes of a is it's actually 14 divided by 11.5, which is 1.22. Okay, so it's exactly what you get. Okay. So in other words, then we are able to see that the centroid of the overall shape, right? The centroid of the overall shape is actually this. The x component is minus 0.348 millimeters. And this one is exactly 1.22 millimeters. So this becomes the centroid of the composite shape. This is how we find the centroid of a composite shape. What is the composite shape? It's this one here. We started here and we had this particular composite shape. We decided to split it into 3 segments, and then we're able to find the area of each segment, etc., etc. And we're able to actually determine the moment arms here. And the moment arms have been determined, and then we're able to find the summations, meaning the x bar and y bar, they give us the actual coordinates of the centroid of the composite shape. Remember that we're dealing with what we call the composite parts, right? In which case, therefore, you have a triangle and a rectangle, and also a missing rectangle that was added here to this. Right, I think that if you look at the time right now, is what? Okay, checking. Right, if you look at the time right now, is just, we can cover more. It's just 11. It's just 01:11 a.m. and we started at exactly 11 p.m. Right, so yeah, it's fair enough. So we have taken like approximately 2 hours 11 minutes. Right, I'm gonna see you tomorrow again, or today. Okay, because it's already morning. I'm gonna see you again at some point. We're gonna fix the time on WhatsApp. Yeah, we're gonna talk about the time and then see how much we can do. Any question on these things so far? Any question?